Another Jacqueline Tyler paper then, TMUA set D paper number 2. So yeah, let's get into it. So it's a differentiation question, so of course we'll expand this top bit, then divide everything by x to the power half, so just taking away a power half from all of these powers, which gets us this, and then of course we differentiate this times this times this, and so on. Don't forget about the plus at the end of that. Put in the point 1, and of course putting in the point 1 is great because it just means that you add the coefficients 3 plus a half plus 3, which is this here. And so we're looking for something that has gradient 13 over 2, which could be either of these two, which is annoying. So we actually have to find out the full equation, I guess. So, I mean, at this point, I put in 1 to the original curve, which got me minus 3 as the y coordinate. So then I can set up y equals mx plus c, or y minus y1 equals mx minus x1. Either of those are fine, and we eventually end up with this here as our answer when we rearrange that. So yeah, that's cool, and we're done. And question number 2 then. So a good use of trinomial expansion here, of course. We want, when we expand this out, we want 3 of the x terms. We want 1 of the y squared terms, because that will give us y squared. And if we've got 3 of those, 1 of those, and there are 5 things or 5 brackets, that means we need 1 of the ones as well. So okay, cool. So we need 3 of these, 1 of those, and 1 of those. And we've got 5 brackets, so the formula for trinomial expansion, and I've got a video on this just in case you want to watch it, but it's just 5 factorial over this factorial, this factorial, this factorial. That's just the coefficient. And then, of course, if you've got any coefficients coming with you from the bracket itself, then you use them. In this case, we don't. So here we're just going to do 5 times 4 because everything else cancels, which is 20, and that'll be that done, and we'll move on. I would suggest drawing this whenever you see it, of course. Minus 4, 2, minus 2, 4 is up there, and then 6, 0 is down here. These are opposite vertices of rhombus. So let's just guess the rhombus sort of goes in this direction over here, like this. I guess it could do something else, but this seems like a pretty good guess because D lies on the y-axis. So I'm sort of imagining this as being A, B, C, D, and then D is on the y-axis. That seems to make some sense to me. I mean, I can now say that the midpoint of these 2 points, the two I've actually got, is obviously, what, 2, 2, wasn't that? Cool. And then we can also, I mean, I don't even know whether we needed that, because of course we can work out the gradient from here to here, because it goes down 4 from this 4, and then across 8 from minus 2 to 6, is gradient minus a half. Rhombuses are one of the quadrilaterals that have its diagonals perpendicular to each other. So this gradient must be 2. I've got a video about all the properties of quadrilaterals, so I'll also plug that as well. You should probably watch it. But anyway, this gradient is now 2. And I think we can work out the coordinates of B now just by sort of process of elimination, I think. Because if we're at 0 here and we know this gradient is 2, we must go across like x and then up 2x because of the gradient 2. But of course, we also must go through 2, 2. So we may as well start here, right? And they go, okay, we can go across 2 here up 4, and that lines perfectly with this. So therefore, that would be good. I think this also works, right? Because that's across 4 up 8 to get to here. But then if you go back the other way, you pass the y-axis. So across 2 down 4 and across 2 up 4 will be the places to go. And I think this will be our answer. So making use of the answers there really helpful rather than just trying to work it out directly. So if a positive integer n has the property that n squared is divisible by 9, so we should work out n squared of these things to see whether they even meet the condition. This does because n squared is divisible by 9. Then n is divisible by 6, but n isn't in this case, so this is a counterexample. If we square 18, we get this, which is also, no, is this? Yeah, this is also divisible by 9, but then this is divisible by 6. That's not a counterexample, it's doing the thing. And then this squared is also, the way that I'm checking these are divisible by 9, by the way, I should say, is because all the digits add up to a multiple of 9. So these add up to 9, these add up to 9, these add up to 9. So yeah, that's a super quick check. And then of course this is also not divisible by 6. So 1 and 3 are both counterexamples to that statement. Trapezium rule then, so I decided to draw this. I know there's a formula for trapezium rule, but without the formula book, I'm not going to remember it. So I just had to do this by hand. So from across from 0 to 1, obviously in 4 strips, we're going to go a quarter, a half, 3/4, 1. And each of these are going to be trapeziums because this goes through 1 on the y-axis when you're at 0, of course. So here, this trapezium is 1 high there, 16 to the power quarter here, and 16 to the power quarter, by the way, is 2, of course. So you add those up, divide by 2, and then times by the width of the trapezium that you're looking at, which is a quarter. So I'm kind of drawing imaginary trapeziums in my head here, and then just working them out using a plus b over 2 times h, where h is this distance across because the trapezium is on its side. Like I said, this is 2, so this is 1 plus 3 divided by 2 times a quarter. which is 3/8. And then we just do the same thing here, right? But this time it will be 16 to the quarter here and 16 to the half here, which is 2 plus 4, I think. So we'll get this, and then same thing for the next trapezium, which is this one, and same thing for the last trapezium, which is this one. And then, of course, we can just add up our results. And I think making them all denominator 8, we can end up with this as our answer, hopefully, before we move on. The first thing to notice about condition A is that k equals 1 works because, of course, sine x is symmetrical over 0 to 2 pi. Its integral is going to be 0. So this cannot be sufficient for B because it's true for k as 1. So it's not sufficient to conclude that B is an even integer because of this counterexample. So we'll get rid of the sufficient statements. And then is it necessary? Well, yeah, because if B was an even integer, this would definitely be true. Because we're just scaling sine down in even powers, so we'll just be doing those two humps more and more often, but they'll still cancel each other out. So I think A, that it is necessary, is going to be the answer. Good, so we all know that there are an infinite number of primes, so I can say for sure that the answer is definitely C, D, E, or F, because the statement is true. It's just whether or not this particular proof actually works. Assume there are finitely many primes, so it sounds like the standard proof. Let the largest be p, let n equal p, but 2p plus 1. Consider this is not divisible by p. It's not divisible by p for sure because of this plus 1, and p is bigger than 1. So, okay, that's fine. Therefore, n is a prime number. The problem is that you haven't checked n against all of the other primes that you've got below p. So, for example, here, let's just do this, assuming that we think the largest prime number is 7. And then, of course, 2 times 7 plus 1 is 15. 15 is not divisible by 7, but it is divisible by some smaller prime, so it's not prime. So this doesn't work, this line here. So we'll cross out this one. This is why, in the proper proof, you times together all the primes that you have, then add 1, because then you're dodging all the primes that you have, rather than just the biggest one. Good, so just some nice log work here. Firstly, these powers of 2 I changed into being powers of 2 so that I can then drop them all to the front of the log. Now, of course, this is useful because, of course, this is 2 times, this is 3 times, this is n times. So we can put all those numbers at the front because multiplication is commutative and just say that it's n times n minus 1 times and so on. So that's n factorial. And then, of course, you've just got n lots of log to base a of 2. So it just becomes this. Now, is that one of the answers just yet? It is, so good. We'll underline C. If not, we'd have to do some more work, but I think it's just straight up going to be C, and we can move on. This is a classic question that you've probably seen before. If we're being honest, Lara states that cards with a vowel on the front have a prime on the back. So obviously you have to check E, because if it doesn't have a prime on the back, then Lara is clearly wrong. The thing is, though, you also have to check 9, because if you turn over 9 and that had a vowel on the other side, she would be wrong. So you do have to check those two. You don't have to check F because she hasn't made a statement about non-vowels. You don't have to check 7 because even if you turn 7 over and it was like an F, again, she hasn't made any statements about non-vowels, so that wouldn't matter. So E and 9 are the only two that you actually have to look at, and we can move on from there. This is quite a cool question. So considering sets of integers that can be made with this, where n is a positive integer greater than 1, integers in this set are even only if n is odd. Well, we can just look at this. This is just 3 to the power something that's a positive integer. So that's just made up of 3's, which means it's definitely odd. It's just 3 times 3 times 3. That's going to be an odd number. This is definitionally, even as we've seen at GCSE, this is of course odd. Odd minus even is odd, but then when you take away another 1, you get to an even. So this is always even. Like, it's just going to always be even. So this statement's not true because that statement is, it says only if n is odd. It doesn't matter. It's going to be even all the time. Next one, integers in the set are always 2 or more or 2 less than the module of 6. So what I decided to do was just work out a couple of these because I didn't really have any feeling for doing this. So these are the first few, and this here, I believe, is a multiple of 6. So this is also not true. Now, all of these are multiples of 4. So I just decided to say that 3 was probably true and move on, which I think is probably the kind of tactic you should use in TMUA because you don't have a lot of time, really. There is a really fancy way to prove that these are multiples of 4, which is if you write 3 to the power n as this, then you can do some binomial expansion. And again, this is the kind of thing that you absolutely shouldn't be doing in the middle of a TMUA exam. You should just have your examples here and go, well, There's no counterexamples really early on, so let's just assume this is fine. Let's move on. But yeah, if you're going to do this properly, this is a nice little method that Jacqueline provided in the notes. So yeah, you binomial expand it, then you can factor. Then when you take away 2n minus 1 down here, that's just going to cancel this n bit and leave you behind the 2 bits that you had earlier on. So this is the second to last term, I guess. And we can factorize out 2 squared from the whole thing. And of course, this is a multiple of 4 just there, and then these are all integers. So we're all done here. And yeah, it's quite a nice little proof, but it is what it is. Nice function question here. I always really like the functional questions. I think they're great. The obvious thing to do here is shove a into this because you know f of a is b, so you can replace this with a b, and you get this. And now you sit here and you go, well, what else do I put in? Do I put in b? Well, no, because I don't know what f of b is, so I would make no progress. But I do know what f of a minus b is, so why don't I just shove that in? Because then at least in this position, I would get rid of the f of a minus b because I know it's a. So I'm going to replace x with a minus b everywhere. And then this, like I said, is just a, which then cancels and you end up with this, which actually isn't one of these. So I thought I'd gone wrong for a second here until I realized, well, actually, well, now I have minus b. I can just put minus b in here because I know f of minus b is this. And then again, some cancelling happens and you end up with finally one of the conditions. Really nice question. Really enjoyed it. P is the set of prime numbers greater than 3. All numbers in P can be represented in this form. Now, this is a true statement that all primes above, or 3 and above, or above 3, sorry, are 1 less or 1 more than modulus of 6. It's got some really nice proofs to it. You can look them up if you want to. Which of these is equivalent to star? So, you know, it's easy to get bogged down in all the stuff here, but counterexamples are pretty much always the way that we always go, right? So a number is not a member of P only if it cannot be written in this form. Well, 35 cannot be written, can be written in this form, but it's not a member of this set because it's not prime. So here's an example of a number not being a member of P, but it can be written in this form. So this statement can't be true. And likewise, 35 also deals with this statement for pretty much the exact same reasons. Now, number 3 is kind of interesting because, and this is a good one to memorize because it speeds you up a lot. This is the contrapositive statement to the original thing. This is like, if you just write this down as something like if P then Q, this is the statement, if not Q, then not P, which is always true. So we can go no, yes, and we don't have to sit here and try and think of counterexamples. So try and recognizing that case is a really good idea. For these 3 integrals here, I just drew them. So, for example, this one, the behavior changes as x equals 2, right? When x is bigger than 2, this is literally just x into x plus 2, which is x squared minus 2x. So it's just a curve that kind of goes up here, sort of this way. I've drawn it as a line because I was being really lazy, but it should be a curve. It doesn't matter, though, for the purposes of this question at all. In the middle between, well, everywhere else, I guess, this is going to be where this is less than 0 because x is less than 2. This becomes x into 2 minus x. So it's just the same curve but upside down. So we're sort of drawing a quadratic here with roots at 0 and 2, which normally looks like this. But from this point onwards, I've just flipped this bit of it upside down to make this bit of it. And that's all I've done there. So okay, and we're integrating between 0 and 4, which is clearly some positive area. I don't care about it, and I'm not going to work it out. Here, this picture looks a bit different. Very similar idea, though. -2 is where the behavior changes. So kind of everywhere over here, it's just going to behave as x squared plus 2x, which looks like this graph, this bit here. And then beyond -2, it's going to be the same graph, but upside down. So instead of going up like this, it's going to come down like this. And the integral between 0 and -4 is all of this bit, but that's a negative number. So this is going to be smaller than this because this is a positive number when you integrate between 0 and 4, and this is a negative. So this is definitely smaller than that. This one we've drawn before in TMUA papers because over here it's just x squared, which is this, and over here it's just minus x squared, which is this. So it looks like this, and the integral of this is 0 between 4 and -4 because it just balances and cancels. So therefore, this one being negative, this one being 0, and this one being positive means the order is QRP, and we don't actually have to calculate any of the actual numbers, which saves us a bit of time. N is an integer such that n cubed is divisible by 5. Which of the following statements are necessarily true? 5 is a factor of n. Now that is actually true here but simply because 5 is prime. Like if n cubed is divisible by 5, then it has a factor of 5 in it somewhere. But that factor of 5 must exist in n, because when you times n by itself a couple of times, where else are you going to get the 5s from except in the n's themselves? If this question wasn't asking about prime number, this wouldn't necessarily be true, because you could like create a factor of 8 through having n being only divisible by 2, because 3 2's together would give you that factor of 8. But because 5 is prime, it just has to be. So this is true. N cubed is divisible by 125. This is also true because, as I was just saying, n has to have a factor of 5 in it. But then when you times 3 of them together, that gives you at least 3 5s, which make 125. So it must be divisible by 125. If k is a multiple of 5, so let's just go with like 25, which divides n cubed, then n cubed over k is a multiple of 5. So let's just say that n cubed is 125. Then we can say that, and then k maybe is 125 because k divides n cubed, but then n cubed divided by k is 1, and that's not a multiple of 5. So there's a quick counterexample, just kind of making them match rather than having an excessive 5 somewhere. So yeah, cool. I think we're done. Question 15. So which one of the statements is sufficient for all of the other 4? So I just went through these in order and said, well, okay, if x was minus 1 or x was 1, this would be true because x is bigger or equal to minus 1, because if it's minus 1, or x is less than or equal to 0 because it's 1. This is also true just for the same reason, because you could have either. This is true because in either of these cases you're less than or equal to 1. And this is true because in neither of these cases, you're still less than or equal to 1 when squared because you are 1. So because A makes all of the other things true, that's going to be the sufficient one. And we got lucky because the first one we looked through was going to be true. Like just to demonstrate that going the other way, like if you just said, oh, this one's true, does it make all the others? Well, if you say this one's true, x could be like minus 5, which makes this one not necessarily true, right? Like we can't sufficiently conclude this because minus 5 squares is something bigger than 1. So yeah, that would be that. When you're doing these questions where you travel along the outside of a shape, like you're walking almost like you're an ant, and you walk along the sides of the shape, the way to think about these questions is to use the plan of the shape. So here's the plan of a pyramid like this, and we're trying to travel from like this corner here to the corner opposite it. Now in this plan here, if we draw a straight line from here to here, what this line represents is the sort of the crawl from here down to here, across the base, and then up again. Because can you see we're walking through the base at some point? So we're going down the side, through the base, and then up the side, back to the middle here. Now that's clearly not going to be the most efficient route, because we could crawl along the sides sort of here to here, and that's clearly going to be more efficient. So if I draw a different net, did I call it a plan the first time? Is that the same thing? I'm not really sure. But if I draw a slightly different net that still works like this, I can walk from here to here, or from here to here indeed, in the more efficient route. So let's do that. Now we have the length 10 meters. That clearly means this is 5 and this is 5. And now, because these are all edges, these are equilateral triangles, right? Because it's 10 and 10 and 10. So this must be 60, which means this is 60, which means the whole thing is 120. And now we can just do cosine rule. We do need to know cosine of 120 is minus half for this method to work. So hopefully you've gone away and memorized that, I guess. But in any case, eventually we'll get 5 root 3 when we root 3 lots of 25 for our answer. Good. So the iteration question then. So U1 is minus 17. Now, this question is kind of intricate and kind of cool as well. If U1 is minus 17, then that means U2 is bigger than minus 17 minus 7 and less than minus 17 minus 2. So that's pretty trivial, and we can work that out. Now, the problem with U3 is that we don't know the exact value of U2. So at least U3 is going to be, well, we can use the smallest one, can we not? But U2 can't actually be minus 24, and these are integers. So the smallest thing U2 can actually be is minus 23. So therefore, the smallest thing U3 can be is minus 23 minus 7, which is minus 30. And the biggest thing U3 can be, again, because U2 can only go up to minus 18 at most, sorry, minus 20 at most, getting my numbers the wrong round, minus 20 at most, then we can do minus 20 minus 2, which is minus 22 here. And we'll keep playing that game using the least, which would here be minus 29, and here, which would be minus 23, and taking away 3 from the biggest and 7 from the smallest. Sorry, 2 from the biggest, but the biggest is 1 less than this. And then we'll keep going for that until we get to numbers that sort of come to minus 53. So the first one that can do it is U7. That could be minus 53. And then if we keep going, I'm just counting up this row now, we see that the biggest one that could still be minus 53 is this one. So that will be 1, 2, 3, 4, 5, 6, 7 of them for our answer of 7, I think. I'm not sure what this minus x represents. Oh, I'm just saying this is, I couldn't be bothered to work out this end. So yeah, I think there are 7 of them in total. 18. Which of these things is or are true independently? For all real x, there exists a y such that this, well, of course, if x is minus 5, that doesn't work, so whatever. There exists a y such that for all x, this happens. No, like there isn't a single y, like a single value of y that for all x's does this, right? You'd have to go with lots of different y's for all the different x's. For all real y, there exists a non-negative x such that this. Well, sure, when you pick a y value, there will be an x value that does this, right? And then when you pick a different y value, you get a different x value, so that one's fine. Just be careful of the kind of the order that they give those two statements, because they seem very similar, but they are not quite. Question 19 then. So we've got two quadratics here, and we want f dash to be bigger than g dash. So we'll differentiate these two things. And now, the thing about this is, if a were bigger than p, then this number of x's would be bigger than this number of x's. Say this was 4x's and this was 2x's. You could take away these from both sides to leave you with like 2x's over here. But then you could just make x trivially large and negative to disrupt the inequality and make it not true. And so actually a is going to just have to equal p, because you can play that game backwards as well if you made the p bigger. So a just has to end up being equal to p, and a bigger than p is not going to be a necessarily true thing. You can also see this by the graphs, right? If you just make b, c, q, and r all 0, you'll end up with a graph like this if this is just px squared. And if you then have ax squared where a is bigger, you end up with this kind of graph. But of course, over on this section, a being bigger just means the gradient is more negative, which means it's less than the other one. And so it can't be true for the entire thing unless a does equal p. So we'll get rid of this. We can get rid of this. It doesn't talk about a and p, but it does talk about c and r. And c and r, of course, are completely irrelevant to the gradient. So this one cannot be necessarily true at all. Now, this one, I think, is necessarily true because, of course, if you make a equal to b, these two things go away, and you're just left with b bigger than q, which is this condition. So therefore, 2, I think, is the answer. And the last one, a really interesting question. If we add x squared to both sides, what we notice is that x squared plus y squared is, by definition, the distance to where the curve is from the origin. Because if you're here, for instance, your distance to the origin is this value here, which is the x value in Cartesian coordinates, plus this value here squared, square rooted. Right? So this here is the distance from the origin. So now we're just trying to minimize all of this over here. I've already replaced cos squared with minus 1 minus sin squared because, of course, I know exactly where this is going. We simplify. We could consider differentiating this if we wanted to, but it's probably easier to complete the square on this kind of thing. So I took the 6 out from the first two terms, and then I completed the square, and then I expanded the 6 back out again, and I got this value at the end here. So as long as I can find a value of x which makes this whole thing 0, the minimum value of the distance will just be 5 over 2. Except that will be the distance squared, I should have said, right? This is r squared, right? So I do need to root 5 over 2 as well, which I think will give me, if I times by root 2 over root 2, root 10 over 2, which is a half root 10. And so yeah, I don't know why I typed another sign here. That is disgusting of me. It's supposed to be this. Who cares? Whatever. This is going to be the answer, and we're done here. Thank you so much, to Jacqueline for writing the paper. I should have said that earlier. Her website is probably below, as long as I've remembered to do that.